Okay, here's a 101. They want us to just find a value that would show that this identity is not always true. Now, sometimes it's true. It's just not always true. So, first of all, if you think about it, um, I could simplify this. Cosine theta, um, they're basically saying this is an identity. And if you think about it, it makes sense because 1 minus sine squared is cosine squared theta, right? So it would make sense that if I took the square root of cosine squared theta, I would get cosine theta. You might think it would always be true, but it comes down to the signs. That's why I wrote this all students take calculus over here. When you square root something, you could either have a positive root or a negative root. So if you just are looking at positive roots, it's going to look like it's always true. But what if you had something that had a negative root? What if you took, you might have cosine theta on this side and negative cosine theta over here, and it might not be the same value. For instance, let's look here. The cosine of 60 degrees is a half, okay? But what would the negative, what would happen if I were looking at something that had a negative cosine? Let's see. If I looked at the negative root of that, this would be a half, but this would be negative 1/2. So if I look at the negative root of any angle, it's not going to be true. It doesn't really have to do with all students take calculus, I guess, so much as when I square root. I have a positive or negative root. And if I choose to look at the negative root, the two sides are not going to be equal. That's really all this boils down to. It really doesn't have anything with all students take calculus. At first I thought it was going to, and then now as I'm thinking about it, it just has to do with what happens if I take the negative root and look at it. As long as we take the positive root, it would be equal. But if we take the negative root, not equal. Okay, so number 11, they give us a function, and then they tell us the rate of change of the function is this cosecant x cotangent x minus cosine x, okay? And so they want us to show that expression that I circled in red can also be written as, I'll circle it in blue, this expression. This is really an identity, and just written in a different form. They're wanting us to show that the red expression is equal to the blue expression. Now, if you notice there's a little symbol out in front of this, that means it's like a calculus-related problem. In calculus, I couldn't integrate the first red expression, but if I changed it to the blue expression, I would probably be able to integrate it. And also, here's the other thing that has to do with calculus here. The rate of change of a function is the slope of the function. And I can find that in calculus, I can find the slope by doing something called taking the derivative. So if I took the derivative of this function f of x, it would be equal to the red expression, which they say is also equal to the blue expression. So it ties in with calculus. Let me start with the red expression. Cosecant x cotangent x minus cosine x. Okay. I'm going to guess, if I'm going to turn it into this other function there, I'm going to try, I'm looking at this, I'm not really seeing any place to go with this. I don't see an identity, but then I don't have my identities in front of me, so I'm kind of working this without it. I am going to guess that what we're going to do is let's try rewriting everything in terms of sine and cosine. Cosecant is 1 over sine x. Cotangent is sine over, it's cosine over sine. I have to flip it, don't I? Cosine x over sine x minus cosine x. Okay, let me kind of simplify that. All right, that's cosine x over sine squared x minus cosine x. This might be a little easier to work with. Now again, I don't know where this is going. I do know that when they started off with the red expression, it was 2 terms, and now in the blue expression, they've got it down to 1 term. So let me do this. I know that I could put, if I got a common denominator, I could put the 2 fractions together. So let me try multiplying. If I put this over 1, my common denominator would be sine squared x. So let me multiply the second term by sine squared x over sine squared x. Again, I'm playing here. I don't have the answer key in front of me. So I have cosine x minus cosine x sine squared x all over sine squared x. Okay, now look at what I've got now, and it is one fraction. I'm noticing that maybe I could do something next. I noticed, well, maybe I could factor a cosine x out of each term in the top. So there's a GCF on the top of a cosine x, and when I pull it out, I have 1 minus sine squared x left, and on the bottom I have sine squared x. Okay. Well, you know what? I know what 1 minus sine squared x is. This much right here, that's cosine squared x. So let me say, okay, I have a cosine x, but I'm going to substitute cosine squared x in for this 1 minus sine squared x, because that's a Pythagorean identity. Sine squared x plus cosine squared x is 1. So 1 minus sine squared x would be cosine squared x. And now I got that all over sine squared x. Okay, I'm almost done. If I look, cosine squared over sine squared, this part right here, if I'm looking at where I'm headed, here's a cosine x, and I got my cosine x, right? I need a cotangent squared x, but that's what this is, isn't it? Cosine over sine is cotangent, so cosine squared over sine squared would be cotangent squared. So this would be the same thing as cosine x times cotangent squared of x. And I'm just going to try to cram it in there. Anyway, so that's what we would do. It's just another way to say an identity, but they're trying to put it in a way that make you think, oh, this might have something to do with calculus, and it does. The rate of change of a function is its slope, and we also call that the first derivative in calculus. And so they're just kind of giving the parts names. It really doesn't, we don't need to know any calculus to work this. It's still very much just working identities.